Morning, everyone. So far in this chapter, again, our key concept is to measure the rate of a reaction. Rate, as you've seen here, I'm just going to keep rehashing this here. Rate is dealing with a change in amount, some physical quantity that changes, but it has to be a time rate of change. It has to be divided by some unit in time. In our first lesson, we talked about here actually converting the rate from one chemical, maybe it's in moles per second. I want to convert over to liters per hour in another chemical. We saw a little bit of stoichiometry work its way back in. In yesterday's lesson, we started looking at what are some possible properties for this change in amount. This Warmup question here is going to start addressing that feature. And then today's lesson, we're going to do our main concept on what's called collision theory. What does the rate actually depend on? And knowing that, is there a way for me to actually speed rates up or slow reactions down? So let's just start off with a quick warm-up here. I'm going to give you a reaction. So we have Cu, it's a solid. It's going to react with 4HNO3. This is an aqueous. This becomes CuNO3 that one there is also aqueous. We have 2 water. Water, we usually don't say aqueous. It's not like water dissolved in itself, so it's just a pure liquid. It's just L. This is 2NO. The NO here is a gas, and this reaction here is exothermic, so we're going to have a heat term. What I want to know here is I want you to state 3 ways to find or monitor the reaction rate. Again, I encourage you just to pause it. You can try it out for yourself, looking at that reaction. What are some physical characteristics that I can set up meters? How can I set up the system? Can I track mass changes, pressure changes, color changes, things like that, so I can measure the rate? There's no one way that's better than another. It's just saying, based on this reaction, can you give me some examples? All right. So, assuming you've done that here, you can check your work with me here. We started off looking at a mass change. For mass change, we're looking for either one solid or one gas. Well, this is perfect. If you wanted to do a mass change, so the first one here, let's deal with a mass change. There's still 2 ways of doing it. I can actually track a mass of Cu lost over time, right? So this is my experiment here. Let's imagine you have a beaker, right? I'm going to take a pair of tweezers. I'm holding onto the copper. At 0 seconds, I know how much my copper is. I'm going to drop my copper in for maybe 10 seconds of time, let it bubble away. I'm going to pull it out. I'm going to dry it off. I'm going to weigh it, drop it in for another 10 seconds, and so on and so forth. I can track how quickly that copper gets lost. That's a change in mass over change in time. So definitely a rate. Perfect. Is there another way I can do change in mass? Well, of course. In this case here, I look at all the states here. Oh, I actually only produce one gas. So if, like in my very first lesson, if we're in an open system, pretty much all the mass here should stick around here. The only reason why my total mass of the system would drop is because the NO is actually escaping. The NO as a chemical is actually leaving the system. That's actually going to take away mass from me. So in this case here, we can track the total mass decrease due to NO leaving. Right. Between those two, both of them measure mass change. Both of them would need scale. I would say that second one is a little bit easier. If you remember that the total mass here still includes the beaker and the aqueous afterwards, we're just looking for the change though. Any drop is due to just the NO. It's the only one gas, so I have the rate as expressed just for one chemical. I can do stoichiometry and I can link it to any of the other variables. Right. Towards the end of yesterday's class here, we talked about here copper plus 2 specifically, right? So copper plus 2 here. Copper plus 2 is actually blue in solution, right? So most of our reactions have just been colorless here. In this reaction, I'm actually taking a solid chunk of copper, so sort of like a bronzish, brownish kind of color. As you drop in an acid, it's bound to create more copper plus 2. So what's going to happen is I'm going to create more and more blue particles. So if I use that spectrophotometer, that was the name of the device, we can actually track the change in color intensity. So color change. I can track how quickly increase the blue intensity due to having more Cu plus 2 ions. And again, concentration at the end of the day, this color is a concentration quantity. It's just that we do have a meter to actually track the color intensity, track how blue the solution is getting. So yesterday it was copper was dropping. In this case here, copper is increasing. That's fine. I can track any changes in intensity. Right? What else can I do? Sort of always a catch-all. If I have this reaction here being exothermic, I expect the system to be releasing heat. If I stick a thermometer in it, I can actually track a temperature change. And in this case here, I expect, because the reaction is exothermic reaction releases heat. So therefore, the temperature increases. Whenever we talk about temperature, we are always surroundings. Like a thermometer here, it's not microscopic enough to actually see what the particles themselves are doing, but the surroundings end up getting hotter because heat is steadily being released. Right? Any other ways that we can do this? Measure the rate. I can think of at least one more way here. Again, we're dealing with an acid. It's not quite a neutralization because it's not acid react with base, but definitely I start off with my most acid solution. So I have a whole bunch of H pluses here. As time goes onwards here, as copper actually reacts away with it, the H plus actually becomes water. We steadily lose H plus because we're losing acidity. So we can actually track acidity change or pH change. In this case here, we're actually losing H plus, so the pH is increasing over time, right? And how quickly that ends up happening, we end up getting the rate. Again, this is just some confusing terminology here. pH is just a ruler. pH is the meter. It could measure acid or base. The smaller the number, actually, the more acidic it is. So in this case here, when we say pH increasing, we're actually saying less acidic, which is what's happening because I'm actually losing the acid here. And in fact, with all these different ways here, again, for this particular reaction, there were so many different ways, I can actually plot this out graphically. And we had done a graph here on the very first lesson with sort of mass change. I can do this, let's say, acidity change. I can track, let's say, here's the pH as time goes onwards. Again, I'd take a few readings, whatever my pH meter says, at a few different, probably even increments, just so that I can take down more data points. I would imagine as I steadily use up my H+, I would expect that the pH here would steadily climb. Now, most reactions here will be fast at the beginning and slower afterwards. We're going to get a way to actually explain that in today's lesson here. In a similar fashion here, we can track temperature change versus time. So again, we can plot temperature versus time. Being an exothermic reaction here, again, I am the surroundings. So basically this one here would increase as well. That's another way of sampling the rate. So all of these can be plotted on graphs here. And because the property is always on the y-axis, whenever I have a change in property, so this is change in pH versus a change in time, I did a rise or a run. Just remember on these graphs here, the slope is the rate. The slope is how fast the reaction occurs. Right? So today we're going to switch over here and we're going to study what does this rate here depend on? Right? What's actually controlling which reactions are fast, which reactions are slow? And in knowing that, we're going to see if we can actually change the speed. So this section here is known as collision theory. They really like asking questions from this portion. So I'm going to highlight some of these features here. Let's study a reaction here between H2 as a gas. It runs into Cl2 as a gas, and this ends up becoming 2HCl as a gas. All right, so there's my reaction as proposed to you here. If I start off with the hydrogen in one container and the chlorine in another container, is any reaction going to happen? Well, no. So the hydrogens here, they have no idea they're beside a chamber that actually has chlorine, and vice versa. Chlorine doesn't know that there's actually hydrogen inside. So that actually gives us some indication here. For a reaction to occur, at least they have to be in the same container. And what's actually happening here is, if I put them in the same container, let's now sort of mix the containers together. Now the hydrogens and the chlorines can actually interact with each other here. For a reaction to occur, particles must collide. They have to be able to see each other. They have to interact with each other. And there's actually two features to make this collision here successful. There's a lot of collisions here. They just bounce. They just come in, they bounce, and they just bounce off each other. There's no reaction. Particles must collide with, and here are the two features that they always like asking you. This is the two features that we're always going to come back to. First one, there's always a little bit of an energy requirement. So how we're going to frame that here is, for a reaction to be successful, you need to have sufficient energy. For sufficient energy here, we can say the reactants must be moving fast enough. Right. We're going to talk about that as a kinetic energy. They have to be moving fast enough to overcome what's known as the activation energy barrier. Think of it as there's an energy hill that if I'm not moving fast enough here, the bonds won't break. I can't switch bonds. I can't end up creating my products here. No reactions. That's one feature. Let's study that one in a little detail here. So basically, I have a hydrogen and a hydrogen. It's supposed to be colliding with the chlorine and chlorine. Those are my reactants. I want the collision to occur. So I want the hydrogen to physically run into chlorine. And basically what ends up happening is the H has to then create a new bond with Cl. And again, this H here has to create a new bond with Cl. It doesn't break spontaneously though. That bond there was keeping hydrogen stable. This bond here is keeping chlorine stable. The energy requirement, that when I overcome this activation barrier, part of that energy is needed to actually break this bond here. I need to be able to separate hydrogen from hydrogen. And not only that, I need to be able to move the electrons close enough, and I actually need to be able to create new bonds between hydrogen and chlorine. So overcome activation barrier, I need to be breaking some bonds, and I need to end up forming bonds as well. And what's going to end up here is it's only the really lucky, the fast-moving hydrogens and the fast-moving chlorines that have enough energy, that come in with enough oomph to actually get over this hill here, right? I can actually plot this on a potential energy diagram. We're going to see this a lot more in tomorrow's lesson. We're going to plot the potential energy versus as time goes onwards. And what we're going to do is we're going to do an interplay between sort of kinetic and potential energy. So far, for kinetic energy, if you remember, kinetic energy is the energy of motion. Moving things have kinetic energy. So what's happening here is I have two really fast-moving particles. They have a lot of kinetic energy. As particles approach each other, so as particles approach, they slow down. They slow down due to repulsion. Why is there repulsion? Well, as the hydrogen is going to the right, chlorine is going to the left, the first things that encounter each other are the electrons on each of them here. Well, as they get too close, now they're zipping by, they're actually traveling really quickly. But as the electrons start getting too close, the negative really doesn't like the negative. They're actually going to apply a force, as actually a repulsive force, try to keep these two things apart. Now, it's not like the hydrogen and the chlorine just stop dead in the tracks, right? They're actually moving really quickly. All that's going to amount to, it's going to take a little bit of time. They're going to experience a force that's trying to slow them down, but it's going to take a little while as this collision happens. Because they slow down, what's going to happen to this kinetic energy? The kinetic energy has to drop. We know from our science courses, energy has to be conserved. Where did that energy go? It can't have disappeared. What I've actually done is I've actually traded that kinetic energy over into potential energy. So as I trade over to potential energy, here's what's happening. I start off with my reactants. My reactants have some energy. My products are supposed to have some energy here. What's happening is when our particles are on a collision course, they start trading some of their moving energy. They start trading it over to what's called potential energy. Potential energy, PE, is representing a stored energy. Basically, what ends up happening is they end up climbing. They end up potentially getting from reactants to products because products actually have higher energy. And in fact, what's happening here is there is actually an energy hill, an energy barrier that's even higher than the products. Only the ones that are moving really, really fast can trade in enough kinetic, can climb this energy hill, climb this mountain to actually get over to the other side. Let's imagine the contrast. Let's imagine we have a slow particle and a slow particle. Because the particles are traveling really slowly, we don't have a lot of kinetic energy. If I don't have a lot of kinetic energy, sure enough, as I zip close to each other here, I'm going to slow down even slower. I trade a little bit of kinetic energy, but I didn't have that much to begin with if I was slow to begin with. All that's going to happen is I'm going to climb the hill a little bit. I've already collided, and now I have no more kinetic energy to trade in. Nothing happened because I didn't overcome this energy barrier. So what's going to happen is after they collide, they just bounce off each other. That same repulsion is going to keep pushing away from each other. We're just going to fall back down this way, and we're sort of stuck on the reactant side. It's only the ones that are fastest moving that can actually get over this hill. More on this in tomorrow's lesson. The one other feature here, so we need to have collisions. For it to be successful, it needs to have enough energy, sufficient energy. The other one here, which may not be super obvious, is they usually refer to this as we usually need to have a favorable geometry. I've seen this being written like they need to come in with a proper angle of hit. I actually care about sort of what orientation things actually come in at. So if you look at this reaction here, if you look at where the H and the Cl are supposed to create a bond, this is probably the best geometry because the top H is close to the top Cl, bottom H is close to the bottom Cl here. What would happen if my hydrogen, let's say my hydrogen was actually like this, was actually zipping towards the chlorine. Let's say these ones here are moving fast enough, they could potentially react. You'll notice what's happened here is, although upon collision, maybe this H would be close enough to one of the chlorines, the other H here is nowhere near close enough to bond with the other one. So what's going to happen here is this is bad geometry, and with bad geometry, what's going to happen is I need to actually take a little bit of extra energy. I need to twist this molecule so that the hydrogen actually is oriented sort of parallel to the Cls so that they can actually collide a little bit easier. So in that case there, extra energy is required to rotate, in our example, rotate the hydrogen if the orientation is bad, right? If it's not keeping the atoms close to the ones that they eventually want to collide with, right? I need to have extra energy. All that's going to do is it's going to make the energy hill even higher. You need to be even faster to get over this energy barrier, right? So I just wanted to introduce that concept to you. That's called collision theory. That's actually the feature that actually controls the rate. And what we're going to do now is we're actually going to look at some common things experimentally I can change in actually changing the rate. Up to this point, we've just been talking about how do I know the rate? How do I measure the rate? This time, maybe the rate is way too slow. What can I do to actually increase the rate? We're going to be looking at these two features again and again. Am I doing anything to the energy argument? Am I doing anything to the geometry argument? So those are the two features that have come back again and again. Let's just step right into it here. So these ones here are these are factors affecting rate. So now that we know, well, collisions have to be successful, they need to come in with good geometry, they need to come in with the right energy here. What are some things I can change to try to speed things up or slow things down? First thing that comes to mind is usually temperature. Right? Now temperature, I would call this, sure, temperature is a factor. I still want you to specify, am I increasing temperature or decreasing temperature, right? Because I would expect that to be opposites. For temperature, usually heating, or you say increase in temperature, heating the system increases the rate, right? And rate and time are sort of inverse to each other. You can also talk about increases the rate, decreases the reaction time. Right? Rxn is just reaction, right? So this is just a generalization. You will find maybe the odd exception. When you heat things up, sometimes it actually slows things down, but for the most cases, it speeds up. Right? Increases the rate, speeds up. Right? So let's take a look at which criterion did I actually change to actually explain that. So let's start off here. Let's say I have a solution. Maybe this is my acid, just waiting for the zinc to be dropped in. Right now here I have a cold beaker. What's the difference between my cold beaker and my hot beaker? First thing, what's the same about them is maybe I have the same concentration. Maybe I have the same everything else. But what's different here is in a cold beaker, because the temperature is a measure of the average kinetic energy, in this case here, it means we have slower particles. Again, we're going to come back to this in a little more detail later on, but basically these particles are just sort of dragging their feet a little bit here. They're not moving all that quickly. For a hot container here, these particles are really zipping by. They're really moving really, really quickly. We actually have a lot of energy. So in this case here, we're going to drop in that same piece of zinc, drop it into the cold, drop it into the hot. It's not impossible for the reaction to occur here, but let's think about those requirements here. For a successful collision, you need good energy, you need good geometry here. In this case here, I've actually changed the energy argument. So under this hot beaker here, I can say a higher temperature means more particles are traveling quickly, right? So all the particles themselves are traveling quickly. And in that case there, we have more particles, not by number, right? The same number of particles as hot and cold, but more particles have enough energy to overcome that activation barrier, to overcome that energy requirement just to get things going. They came in fast enough, they can trade in enough kinetic, they can climb the energy hill. Because I have more particles that can do that, we have better chances of successful collision. So that's the first feature here. Second feature we can think about here is concentration. Right? So for concentration here, again, concentration is the factor. Usually, generalization here, usually a higher concentration means a faster rate. Right? Smaller reaction time. So let's start off here. If I have a container that's not really concentrated, maybe it's 0.1 molar HCl, so very low concentration. Right? Let's compare this container here to a container that has very high concentration, so lots of HCl, so maybe 6 molar or 12 molar, really, really strong, so really, really concentrated. I'm going to drop in that same piece of zinc. I'm going to drop in that same metal. Because for a successful collision, you need to have good energy and good geometry. First thing I'm going to emphasize here is concentration has not affected the energy in the slightest, because I would imagine these are at the same temperature. So I'm going to make that note there. Because we have the same temperature, the energy is similar in both beakers. So this time it's not the energy argument. That only leaves you the geometry argument here. Well, for a successful collision, for a successful reaction to occur, we need things to collide, and they need to collide with good geometry, the good angles. They need to be close enough to actually, for bonds to form, for bonds to actually break. Not only do you have more collisions in high collisions, so because same temperature energy is similar in both beakers, higher concentration means more collisions. Now, what's important to note here in this feature here is it's not just the sheer number of collisions. They've done a calculation. They've said just because of the number of collisions, right? There's more particles. There's going to be more hits in this higher concentration beaker here. Just because of that, the rate would only increase by about 1%. Okay, it's not much. In fact, here, because there are more collisions, this next part is important. Higher concentration means more collisions. So we have a better chance of collisions with favorable geometry. So we have a better chance of them coming in, the particles are close enough together so the correct bonds can break, the correct bonds can end up forming. Correct geometry here, no extra energy to actually twist the particles there. Other ways you can say that here is higher likelihood, so higher chance, likelihood. Higher likelihood of good orientation. So I didn't touch anything in terms of the energy requirement because we're at the same temperature, but we're actually just increasing the likelihood of having better geometry. That was the other thing I needed in collision theory. I'm actually going to throw in surface area as a sort of side note. Surface area at the end of the day, it does end up as a concentration argument. I'm going to show you to you in pictures here. But for surface area only affects what are referred to as heterogeneous systems. What heterogeneous means here, hetero means that they're different. In this case here, it means my reactants are in different states. So one is solid, one is aqueous. That's what I mean by state. So if you imagine here, let's take that solid chunk of zinc here. It's just a nice, like one piece of zinc. In this case here, because I need collisions to actually occur, you're going to realize in this low surface area argument here, there's only so many zinc that can actually run into the acid on the outside. In some sense, those internal internal zinc particles here are actually not actually able to collide yet. This is heterogeneous because in this case here, my zinc is solid, and we have my solution here is liquid or even in the aqueous state. What if I increase that surface area? So what they like saying here is they like using the terminology of powdering. So what if I cut this piece of zinc here into little bits, little pellets, little shells, there's like that? In that case there, it may be the very same number of zinc particles, but instead of some of the zinc actually being locked away, more of the zinc is actually exposed, and now the acid can actually react with more particles. And again, exactly the same argument here. When I have an increased surface area, you can say there are more particles exposed for collision. It's not just the sheer number of collisions, you have to still emphasize, so better chance of colliding with good geometry. This whole chapter just always comes back to those two features. Did I do anything to the energy? Did I do anything to the angle? Based on that here, we can actually make a general note here. A general reaction rate kind of problem here. We would expect solid to solid kind of reactions to be slow because the particles here, they're all locked away, they're all really tightly packed together. We'd imagine liquids to be a little bit faster than that, right? Liquids, the particles are slipping and sliding. We'd imagine that gases are even faster than that. And surprisingly, we're actually going to have aqueous, actually the fastest of all. Now, usually I'd say, well, what is it about aqueous? Aqueous is sort of like this, where particles are actually dissolved in solution. Why is aqueous even faster than gas when gas already has the most energetic particles? They're colliding really hard, really fast. It's true. It's sort of a toss-up between gas and aqueous. What I would argue for aqueous is, for aqueous, you're going to have some things that are positive, some things that are negative. Because of these charges that we have, that's actually going to have some control over opposite charges attract, like charges repel away from each other. It's actually going to add another dimension to it where the charges actually want to get close together. And in that case there, it'll actually control how the angle is going to come in with. Because of those charges, maybe I'll make this note here. For aqueous, charges can control the angle of hit to some extent, right? And that's why I would actually specify aqueous would actually be fastest. How that question is usually worded here, with nothing else to bank on, they're going to give you, oh, I have chemical A, it's solid, and I have 2B as a gas. This becomes 3C as a liquid. Compare that reaction to D as a liquid, and 3E as aqueous, and F as a solid. First thing I'm going to ask you in this question here is, which of these reactions do you think would be faster? You are only interested in the reactants. Speed only depends on the reactants, right? Because those are the particles that are trying to come together. They're trying to overcome this energy hill. They're trying to collide with good geometry. So I could care less that later on, oh, it's a solid, it's slow. Later on, it's liquid, oh, it's slow. I'm not worried about that side. I'm worried about on this side here. So in this case here, I have a solid, which I know to be slow. It's reacting with a gas, which should be much faster. But in this case here, because I have an aqueous and a liquid, this case here is expected to be faster. With nothing else to go on, I would imagine that this one here is faster because of that aqueous state. Aqueous has that extra charges to actually control the angle of hit for you, right? So there's that note here on surface area only for heterogeneous reactions. Let's end off here with pressure and volume. I mentioned in yesterday's lesson, whenever we do a pressure and volume, we are specifically looking at gases. These ones here, there's an inverse relationship. This amounts to a concentration argument. Let's see if you can do it for yourself. Let's start off in a big balloon. High volume means low pressure. In a big balloon, your particles are really wildly separated, right? They have a lot of room to stretch out into. What if I try to stress out the system, and what if I decrease the size of the container? By decreasing the size of the container, I've done that by increasing the pressure, by squeezing it. The number of particles hasn't changed. However, because now it has less room to actually collide into, in this case here, again, we're going to have more collisions. So this one here, I would imagine in this second container, I'd imagine this second one is faster. Let's see if you can tell me here. We had two requirements. For a successful collision, we needed the two features. Did I do anything to the sufficient energy argument? Did I do anything to the particle's energy? Or did I do anything to the favorable geometry? Which one of those did I change to amount to, well, if I'm in a small container, there's more collisions. So therefore, which one have I actually changed to therefore speed up the reaction. This one is sort of like a concentration change. We'll do this graphically in the next chapter as well. But basically, you can rely on collision theory for those two. If you have any questions, just let me know. Thanks, guys.